Hello there. This video is on section 2.5, where we're going to determine where a function is continuous or discontinuous. So let me first try to explain what continuity is. And just as an aside, as much as mathematicians claim to be very precise and accurate about things, I find them be a little bit ambiguous or at least vague on continuity. So let me just make sure I clearly define that. So there's two types of continuity: continuity at a point and a function being continuous. And these are not oftentimes distinguished, which it's important to do so. So what does it mean to be continuous at a point? That's where we're going to start right now. I'm going to define continuity at a point. So let's say that point is x equals a. So suppose we have a point where x equals a. I mean, a could be 3 or 10 or whatever, but we're going to give them some initial point. Oops, I said 3, but I want to do a there. Yeah. So suppose we have some x equals a point. To be continuous, so the function is continuous at this particular point if we have the function at that point is equal to some number. The limit as x approaches a from the right of that function is the exact same number, and the limit from a to the left of that function is the exact same number. So they have to be all the exact same thing, and then we say the function is continuous. So all three are equal. And that's what we mean by a function being continuous at a specific point. In order for the function to be continuous as a function, so f of x is a continuous function. So now we're no longer talking about continuous at a point. We're talking about a continuous function. So continuous function, if f of x is continuous on every point, every single point we can possibly imagine of its domain, right? You can't go outside its domain, right? It's not defined to be something, you can't call that not continuous. All right, so that was my attempt to clarify continuity at a point. We need to test these three things right here. And then for a function to be continuous in general, we essentially need to know that those three things are true no matter every single point you choose, no matter what. Now, if I say continuous to a math student, they might have an intuition of what that means. They kind of think, okay, well, continuous means that it keeps going. So we can imagine that the function is continuous if there's no breaks, like if it had a jump, that seems to be not continuous. Or even if there's just a hole in the graph, that would be not continuous. So that's the idea, is we want to avoid those things that you have to like lift your pen off the paper or some jump or skip or something like that. Those would be things that we want to avoid. Continuous means it can just draw all the way. Well, we can't rely on graphs to do the work. We have to understand this at a more sophisticated level. So all of that intuition is very helpful, and it can guide us. We need to actually do some mathematics to determine whether, in fact, it's continuous or not. So let's do some examples. You can see it in action. I'll start off with example A right over here. In example A, we're given a function. It's a piecewise function. We're using a lot of piecewise functions here because it's easy to manipulate them so that they can be continuous or not continuous. And so you'll see that quite often in these types of problems, but it doesn't have to be just for continuous. I mean, for piecewise functions, you can discuss continuity for any type of function. All right, so in this continuous function, we're given the first branch is x squared minus 1. You may know x squared minus 1 is a parabola. So, it's going to be a parabola, normal parabola shifted down by 1. So normal parabola shifted down by 1. And we know parabolas are continuous. This second branch over here is a line, y equals x plus 4. We know lines are continuous, right? So both parts seem to be perfectly fine. There are functions that we know and we've used before, and we know that there are no points in which the value of the function is not the same as the value of the limit. However, this function f of x changes from one branch to the next. So it starts off as this parabola, and then all the way up to 2, it stays the parabola, and then it switches to this line for x, I guess, for x less than 2. It starts with the line and then switches when x is bigger than 2 to the parabola. So we want to know what happens at 2. At 2, it could connect or it could be disconnected. So let's find out what happens at 2. So what happens at x equals 2? That seems to be the only point of interest for this function because everything else is kind of just an ordinary. So if we want to find out what happens at x equals 2, we have to do 3 things. We have to find the value of the function at 2. We have to find the limit as x approaches 2 from the right. And we need to find the limit as x approaches 2 from the left. So we do those 3 things. And if they are all the same, if they all equal the same number, then we know it's continuous at that particular point. Okay, so what is the value f of 2? Well, if you remember piecewise functions, you have 2 different branches. You have to decide which branch to use to calculate things. F of 2 would be the top branch because the top branch says values greater than or equal to 2. So we use the top branch. F of 2 we would calculate to be 2 squared minus 1, which is equal to 3. All right, what about this limit thing? Well, we're doing limit as f of x. Limit of x goes to 2 from the right of f of x. So what does it mean to do the limit from the right? That means we have values that are greater than 2. If I was going to make a table, I would choose numbers like 2.1 or 2.01 or 2.0001. Those are all numbers to the right of 2. So if I'm using numbers like this, which branch do I plug it into? Well, once again, it's the top branch because the top branch says numbers that are greater than or equal to 2. So I'm plugging in 2.1, 2.01, 2.001. This number right here, let me write the function so it's easier to see. I'm going to color code this, sorry, just so that visually it looks a little bit better. So this is the function right here of x squared minus 1. And essentially what's happening is this x is getting closer and closer and closer to 2. 2.000000001 squared is basically, still 4, right? So this becomes 4 minus 1, which is the same as 3. So it matches up. That's very good. We got one last thing to do, which is the limit as x approaches 2 from the left. So these would be numbers that are smaller than 2. So I'm no longer using 2.1 or 2.01. I'm using numbers which are smaller than 2. That might be something like 1.9 or 1.99, things like that that are smaller than 2. If I use numbers like 1.9 or 1.99, which branch do I use? The answer is the bottom branch, because the bottom branch has numbers x smaller than 2. So if I use the bottom branch to evaluate this, then I'm going to have the limit as x approaches 2 of, I think that says x plus 4. Yes, it does. Limit as x approaches 2 from the left of x plus 4, because that's the bottom branch. And once again, this x value is getting closer and closer and closer to 2. 1.9, 1.9999999. It basically becomes 2. And so we get 2 plus 4. 2 plus 4 is 6. So we had the value of the function at 2 was 3. The value from the right was 3. And the value from left is 6. They don't match up. So this is not continuous. So we know this function here is not continuous. So for part A, f of x is not continuous at x equals 2. And in general, if it's not continuous at a particular point, the function is no longer continuous in general, because to be continuous in general, it means it has to be continuous at every single point. We found a point where it's not continuous, so therefore the whole function is not continuous. So that's an example of continuity, testing continuity at a particular point. Let me show you visually what's going on here. I'll move me over there a little bit, or down here. Okay, so in order to type this piecewise function into Desmos, I just created the two branches here and here. Let me change them so they have the same color, because it is the same function. It's just two branches of the same function. So there's the two branches, and you can see visually they really don't look like they connect. This line thing went up to 6, and the parabola goes here to 2, 3. And it looks like it's a line, but if we zoom out, you might be able to see it curves a little bit more, or of course, you can just show more of the function. If we get rid of this x is greater than or equal to 2 part, then you can see the entire parabola like this. But we do cut off, we can use the bracket here and say we want x to be greater than or equal to 2, and that just shows the right-hand side of that parabola, the part where x greater than or equal to 2. All right, so that's kind of hopefully visually what's going on. Again, we want to know what's going on without relying on a graph. They can be deceptive, and they don't oftentimes offer definitive proofs, justifications for our answers. Okay, so back to the lecture notes. I could change the bottom part x plus 4 to x plus 1. Example B, you'll notice, is basically the same as example A. It's a 2-branch piecewise function. The top branch is x squared minus 1 for x is greater than or equal to 2. The bottom branch is x plus 1 instead of x plus 4. So before we had x plus 4, now we have x plus 1. I'm just going to switch that over here in Desmos. So we can make x plus 1 be the second part of the branch. And now visually you can see where they match up. We do have to verify that using our math. So, of course, I've run out of room because I'm very bad at page management. But for part B, we want to find the value of the function at 2, the limit from the right, and the limit from the left. Well, the value of the function at 2, we know that's the top branch. Just like before, it's the top branch. So that's going to be a 2 squared minus 1, which is 3. X approaches 2 from the right against top branch. So just like before, we're going to have x squared minus 1, where x is getting closer and closer and closer to 2. So this becomes 2 squared minus 1, which is equal to 3. And for x approaching 2 from the left, we use the bottom branch being right here, x plus 1. So this is going to be x plus 1, where x is getting closer and closer and closer to 2, but from the left-hand side, like 1.999, something like that. So it becomes infinitesimally close to 2, and 2 plus 1 is equal to 3. And we have the value of the function, the limit from the right and the limit from the left, all equaling 3. So example B, the function is continuous at x equals 2, and we actually think it may be continuous overall because we're so used to these parabolas and line functions. They don't seem to have any problem with continuity anywhere. It's only when we try to match 2 up in a piecewise function that we seem to have a potential problem. So zooming in here, you wouldn't see a break. And in fact, we know this is continuous. We know that they match up perfectly because the limit from the left is 3, the limit from the right is 3, and the value of the function is 3. So that's how these continuity arguments work. So you'll be asked to do some of these. Is it continuous at a particular point? Is it continuous in general? You'll be asked to do some of these problems. All right, well, let's do a few more examples, and I'll show you some slight variations on these, but they're pretty much all that we're being asked to do in this section. Okay, next up is this example C, where I've changed up the functions just a little bit. X squared minus 5 for x greater than 4, and x plus 7 for x less than 4. So for part C, 4 is the point where they switch. It's a parabola, it's a line on the left, I guess, and lines are continuous for the most part. Parabolas are continuous for the most part. The thing we're wondering about is 4. What happens at the 4? So what happens at x equals 4? Well, we do our test, we do our calculations, we find the value of the function at 4, we find the limit as x approaches 4 from the right, and we find the limit as x approaches 4 from the left. Now, for you sharp eye viewers there, you may notice that for F4 to calculate the value of the function, we can't use the top branch. The top branch only applies for values x greater than 4. And we cannot use the bottom branch because it only applies for x values less than 4. So the value of f of 4 does not exist. We use the DNE. I think you're used to that now in the WebAssign homework. DNE stands for does not exist. This is why it's important to test the value of the function. A lot of people focus on the limits, but you also have to test the value of the function. I think these limits are the same. If I'm going from 4 to the right, that's the top branch. So that's the x squared minus 5. And that's going to turn into 4 squared minus 5 because x is infinitesimally close to 4, which is 11. And lastly, I'm looking for x to be there, approaching 4 from the left. For numbers that are smaller than 4, we'll use the bottom branch. So that's the x plus 7 branch. And when x is infinitesimally close to 4, 3.99999, it becomes indistinguishable from 4. So we get 4 plus 7, which is in fact equal to 11. So here we have the limit from the left and the limit from the right are both equal to 11, but it's not continuous at that point because the value of the function at 4 is also not 11. In fact, it doesn't even exist. Well, could we modify this function so that it would be continuous, right? Can we remove the discontinuity at x equals 4? So you'll look perhaps from C to D. D has the same two branches, x squared minus 5 for x greater than 4, x plus 7 for x less than 4. And what would we do when x actually equals exactly 4? Remember, we want this to be continuous. So at the point where x equals 4, we need it to match up with these one-sided limits. So if we make this equal to 11 when x equals 4, then we essentially now have a continuous function because from the left it's 4, from the left it's 11, from the right it's 11, and exactly at 4 it is also equal to 11. So that's how we can remove the discontinuity, is what the math people call it, by adding in another branch to the function so that they all match up. All right, we got one last problem, and then we're done with this particular section's lecture. Part E right here, we have another piecewise function, x greater than 2, x less than 2. And we want to find out what happens, at the interesting point. And the interesting point is 2. That's where the function switches. Although this first function, the first branch, I should say, it's all one function. This first branch is rather complicated. And you may notice that there is a problem with 2 because you can't have 0 in the denominator and have a meaningful calculation for that. So for a couple of reasons, 2 is not the greatest point. I can't think of anything else that would cause a problem. X equals 1, x equals 0, x equals 5, x equals 4. Nothing else seems to cause a problem. They all just give regular values, but 2 is really a point of interest. So in a homework, they probably would tell you to investigate 2, but I left it a little open-ended so you could think about it. What happens at x equals 2? All right, well, let's see if I type it into Desmos. Yeah, here it is right here, x squared minus 4 over x minus 2 and x plus 1. The first branch is for x greater than 2, so let me turn off this other picture, and we'll do this one. Before I show you the picture, I'm going to do some tabling here. So I'll make this into a table. The reason why it says undefined, 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 undefined is because this function, or this branch, excuse me, is only valid for x greater than or equal to 2. So we could put 2 in there, but remember, we can't divide by 0, so 2 is in fact also not calculable. But we could put something greater than 2, like 2.1, right? And we could put something closer to 2, like 2.01. and 2.001. And you might be able to see a pattern now about how it's getting closer and closer and closer to 4. And in fact, the limit as x approaches 2 from the right for numbers that are greater than 2 is in fact 4. We can do kind of a sneaky little algebra trick for this function by factoring it. So maybe some people recognize that. So if we're going to have we have to do the value of the function. The value of the function at 2, because we're interested in what happens at 2. We need to find the value of the limit from the right. From the right, for x values greater than 2, we're going to use this fraction, this rational function. And then the limit as x approaches 2 from the left. For the values of x smaller than 2, we're going to use the bottom part of the function, or the bottom branch. And so you could try to plug in numbers for 2. You could use a table to experimentally see that the limit is probably 4. But we can also factor this thing, if you remember your algebra skills like that. The top factors to x minus 2, x plus 2. And the bottom is x minus 2. So no matter what number, 2.001, 2.001 minus 2 on the top, and 2.00 minus 2 on the bottom, they are always going to divide to equal 1 and 1. So this just becomes x plus 2. But we know that x is getting infinitesimally close to 2. So this becomes x plus 2, where the value of x is getting closer and closer to 2. So 2 plus 2 is equal to 4. So this top limit is equal to 4. For the bottom limit, as x approaches 2 from the left of x plus 1, we would just basically say that x is getting closer and closer to 2 from the left, 1.9, 1.99, 1.999. So that becomes 2 plus 1, which is equal to 3. And the value of the function at 2, well, it doesn't exist because we can't calculate when we divide by 0. So this is a D and E. Right? As much as we can do the limits and say, well, as we approach 2, we can get 4, or if we approach 2 from the other side, we can get 3. It doesn't exist at 2, even though it's defined here. When I try to plug it in, it's not calculable. We get something divided by 0. So this one is definitely not continuous at 2. It doesn't exist at the point we're interested in, and the limit from the left and the limit from the right disagree. So for many reasons, this is not continuous at that particular point. Let me show this, please. There we go. So that's what the piecewise function looks like. You can see they don't match up visually. And in fact, it doesn't even exist at x equals 2. It's not up here. It's not down there. It's nowhere. It's not calculable at x equals 2. So because this function is not continuous at x equals 2, it would not be considered continuous in general. So it's essentially what they're going to be asking you to do. Is it continuous at a particular point? Is it continuous in general? That's what we're trying to get students to understand about continuity in these early chapters of calculus. All right, well, hopefully that was beneficial to you to understand the idea of continuity and to actually how to compute whether or not a function is continuous at a point or continuous overall. Please reach out if you have any questions or need help with anything. And I hope you have an enjoyable day.